Hey everybody, Mr. Smith here. Welcome back. In today's deck, what we're going to do is to take a look at the math of electric fields. And you're going to see a couple of things where we work in the conceptual stuff that we just discussed and where it becomes very important for you. So we're going to dive right in. As you remember, electric field is the entity that reaches out between charges. And so if you were thinking there was a connection between force and electric field, yeah, you'd be right. So here's the formula for Coulomb's law, K Q1 Q2 over d squared. Here's the deal. It's easy enough to work these formulas. What I want to do is to share with you a small teaching point that I like to offer. Q1 and Q2 in this formula are absolutely indistinguishable. They don't really have any personality. But what I like to do as I write the formulas for electric field is give them a little bit of personality. So as you'll remember, we talked about the fact in the conceptual deck that a test charge has to be small because it has to not influence the electric field around it in any major way. So for that reason, what I do is when I use this formula right here, E equals KQ1 over d squared, what I imagine is Q1 is a large charge. And what it does by itself, if you look at the shape of this formula, is to establish an electric field that radiates out into space. So I imagine Q1 as being kind of a big thing, and it causes the effect that the Q2 feels. And then if we come to this formula, force divided by Q2 obviously gives us this guy over here, but the way I think about it is that Q2 is a small test charge. It sort of passively experiences forces. And I like that way of thinking about it because it fits with the language that's usually used in textbook problems about electric fields. So here's one of them. We've got a -1 microcoulomb test charge. He experiences an electric field of 1,000 newtons per coulomb in the I direction. What force does the charge experience? So force is a vector. We're going to want to get the number right. We'll get the direction right. First things first. You see the word experience? That to me means he's a Q2. They didn't give us a Q1. They gave us a Q2. And what I'm going to do is go ahead and solve this thing. They're asking us for the force, so we can take our first formula and just solve it. So electric field times Q2 is going to give us the force, and that's easy enough. So electric field is 1,000 newtons per coulomb, and we're going to go ahead and plug in our 1 microcoulomb test charge, and what this turns out to be is, looks like 1 millinewton, or 1 times 10 to the minus 3 newtons. The thing is that this guy has a direction as well as a size. He's a vector. So what I want to do is just not blow off the fact that directions are important in these. So if this test charge experiences an electric field that's 1,000 newtons per coulomb in the I direction, we'll do this often in class. We'll draw a field and we'll say, well, here's an electric field. It's equal to 1,000 newtons per coulomb and it's pushing it in the I direction. So if I have a negative little test charge out here, what's the direction on the force? Well, you should remember from our first deck that the direction on the charge is going to be to the left. Why? Because it's positive charges that would be responsible for setting up this electric field that moves to the right in the first place. So really the direction on the force would be -1 times 10 to the minus 3 newtons in the I direction. Okay, so a small point, but not that small. All right, another kind of textbook problem. What we've got here is a 1 microcoulomb charge experiences a force of 20 newtons in the I direction when placed 20 centimeters to the left. No big deal, we can do that. What I want to do though is show you the importance of a diagram. So what I do for ones like this is I just draw the geometry of it. So I've got my little test charge, and I knew that was the thing to do because it was experiencing, it's passive, a force of 20 newtons in the I direction. So this guy is getting towed with a force of 20 newtons in this direction. And they ask us, first of all, what's the electric field in the vicinity of the charge? Well, we can do that. That's the first formula. E equals F over Q2. And we're just going to plug that in. So we get F is 20 newtons. Q2 is 1 microcoulomb. And then this turns out to be 20 times 10 to the 6, or 2 times 10 to the 7 newtons per coulomb. So now let's get the second part of that right. What we want to do is get the direction of the electric field. So let's think about it. Why would this positive charge be experiencing a force to the right? It could only be because this charge over here is a negative. And what that means is that the direction of the electric field along this axis is actually cruising inward. So it turns out that the direction of the force is this direction, and the direction of the electric field is actually in this direction as well. Okay? So if you were on this side of the negative charge, it'd be a whole different story. The negative sign would flip. Okay? So we're going to take a break. We're going to go look at the second thing. What's the value of the unknown charge? And we'll just pause here for a second to do that. So to get the second part of the problem, what we're going to do is resort to our second formula, which is E equals KQ1 over D squared. And we're just going to work the little bit of algebra we've got to do. We're going to go ahead and solve this thing for Q1. So Q1 is going to equal ED squared over K. And when we plug this guy in, let's go and see what we get. How about 2 times 10 to the 7 newtons per coulomb. D is what, 0.2 meters. And divided by K. And how this worked out a second ago, it was 8.8 8 times 10 to the minus 5 coulombs. So actually that was going to be 88 microcoulombs. Except, what thing? Was it a minus charge or was it a plus charge? Oh yeah, it was a minus charge. So it was an 88 microcoulomb charge. Okay? So those are your basic couple. So using the two formulas that are the most common for electric fields. So we're going to take a look at another example and then one that we're going to touch lightly. One of the things that separates Physics 2 from Physics 1 is that we use a lot of Physics 1 and we just assume that guys remember it. In reality, they may or they may not. What I'm going to do is give you a hint about a kind of question that will come up. So in this one, we've got a Bohr model of the atom. So there's a proton on the inside of this guy. And what they're asking us about is the forces of attraction that hold this electron in there. And it's a neat question. So what we've got is a combination of electrostatic forces supplying the inward pull that keeps this electron from zinging away. And what it lets us do is to get a little bit of insight about the forces that are going on inside the atom and also how fast the electron might be going if the Bohr model of the atom is really accurate. So let's go and take a look. I've got the force of electrostatic attraction is KQ1 Q2 over distance squared. And so what they give us is, because this is a Bohr model atom, I've got one proton with a charge of 1.6 times 10 to the negative 19 coulombs. And electron has the same exact charge, so we're good to go there. And we're going to divide that by this teeny tiny number, 5.3 times 10 to the minus 11 meters, and we're going to square that. And what we'll end up with is that the force of attraction between the proton and the electron, it sounds small, so I got it over here. It is 8.2 times 10 to the negative 8 newtons. And it is small, but not compared to the size of an electron. The mass of an electron is tiny. So the acceleration the electron experiences is going to be insanely big. Okay, so here's the first answer that we were looking for. We've got the force of attraction now. And what we'll do is just flip the page here and go and see if we can use that to figure out the velocity of electrons. So we had 8.2 times 10 to the minus 8 newtons. Where does that connect with Physics 1? Well, here's the deal. Force centripetal, the inward pulling force that keeps objects on circles, is equal to mv squared over r. And so what we can do is actually just work this formula and solve it for v. So we've got force centripetal times r, all divided by mass, and then we'll take the square root of that whole thing, and that'll give us the velocity. So check out these numbers when they come together. So tiny force, 8.2 times 10 to the negative 8 newtons. And for space, I'll leave off the label this time. Radius, 5.3 times 10 to the negative 11. And divided by the mass of the electron. This is where it goes crazy. 9.1 times 10 to the negative 31 kilograms. And we'll square root that whole thing. Okay? And I did that, and what actually comes out of this, this fraction when I square root it is 2.2 times 10 to the 6 meters per second. Okay, so there you have it. So it's a combination of old physics and some newer physics, and we're using electrostatics as the bridge between them. Okay, one last thing we're going to talk about. All the stuff that we learned when we worked through forces in combinations with the vectors, they all still apply here in electric field. So if you guys as a class want me to work through a problem like this and do a deck on it, I will do it. What I'll just say here is that if they're asking for the magnitude and the direction of the electric field in the vicinity of charge Q3, what we're going to do is isolate. We're going to get the electric field that this guy creates down here. We're going to get the electric field that this guy creates over here. We're going to have to do some vector stuff, and we're going to add them together. And then the math is not really new. You've seen it before. And again, if you want to see that done out, I'm happy to do that. I'm going to ask you to do that in homework. So it's fair if you want to see me work it out. But that's it for now. Bring your questions to class. Take care and see you soon. Bye-bye.